US Physics Olympiad, year 2015, USAPHO. Final exam. Problem A4. A heat engine consists of a movable piston in a vertical cylinder. The piston is held in place by a removable weight placed on top of the piston. But piston stops prevent the piston from sinking below a certain point. The mass of the piston is M equal 40 kg. The cross-sectional area of the piston is 100 square centimeters, and the weight placed on the piston has a mass of 120 kg. Assume that the piston around the cylinder and the piston is a vacuum, so you don't need to worry about external atmospheric pressure. At point A, the cylinder volume V0 is completely filled with the liquid water at a temperature 320 kelvins and the pressure P minimum. That would be just sufficient to leave the piston alone, except the piston has the additional weight placed on top. Heat energy is added to the water by placing the entire cylinder in a hot bath. At point B, the piston and the weight begins to rise. At point C, the volume of the cylinder reaches V maximum and the temperature reaches 400 kelvins. The heat source is removed. The piston stops rising and is locked in place. Heat energy is now removed from the water by placing the entire cylinder in a cold bath. At point D, the pressure in the cylinder returns to P minimum. The added weight is removed. The piston is unlocked and begins to move down. The cylinder volume returns to V0. The cylinder is removed from the cold bath. The weight is placed back on top of the piston and the cycle repeats. Because the liquid water can change to gas, there are several important events that take place. At point W, the liquid begins changing to gas. At point X, all of the liquid has changed to gas. This may not occur the same as at point C described above. At point Y, the gas begins to change back into liquid. At point Z, all of the gas has changed back into liquid. When in the liquid state, you need to know that for water kept at a constant volume, a change in temperature delta T is related to change in pressure delta P, according to delta P approximately equal 10 power 6 Pascal per Kelvin multiplied by delta T. When in the gas state, you should assume that water behaves like an ideal gas. Of relevance to this question is the pressure-temperature phase plot for water, showing the regions where water exists in liquid form or gaseous form. The curve shows the coexistence condition, where water can exist simultaneously as gas or liquid. The following graphs should be drawn on the answer sheet provided. Question A. Sketch a PT diagram for this cycle on the answer sheet. The coexistence curve for the liquid-gas state is shown. Clearly and accurately label the locations of point B through D and W through Z on this cycle. Question B. Sketch a PV diagram for this cycle on the answer sheet. You should estimate a reasonable value for V maximum. Note the scale is logarithmic. Clearly and accurately label the locations of points B through D on this cycle. Provide reasonable approximate locations for points W through Z on this cycle. Here are solution diagrams for this problem, and let's explain them. First, we start by computing pressures. The minimum pressure is when only the piston is to be lifted. So we have P minimum equal weight of piston mg over cross-sectional area A, which is 40 kilopascals. The maximum pressure is when lifting the piston plus extra weight, and the extra weight is 120, so total is 160, and P maximum will be 160 kilopascals. And point A is clearly at P minimum and T0. For liquid water, a small temperature increase results in a large pressure increase. So point B is effectively at the same temperature as the point A. Process A to B is therefore essentially isothermal, and it is also constant volume process. After that, the pressure is sufficient to lift the piston plus extra weight, so the volume expands at a constant pressure for the process B to C. However, liquid cannot change to gas until we reach the coexistence curve. This defines the location of point W on the PT graph, where are stuck on the coexistence curve until all the liquid has changed into gas. So X and C are also at the same point. It is expected that the examinee will know that liquid water will only expand slightly when heated over the temperature range. So point W must be very close to V equal V0 on the PV diagram. Upon reaching C, the piston is locked in place, constant volume, and the cylinder is lowered to cool. To figure out what happened, consider the ideal gas law. PV equal nRT. For a constant volume process, the temperature of the gas is proportional to the pressure, implying that it would follow a straight line toward the origin of PT. But this forces us back into the liquid region of the graph, so instead we must follow the coexistence curve down, immediately changing gas back into liquid. A such Y is at the same location as C and X. The next process, C to D, is a constant volume, but not isothermal. On PT graph we follow coexistence to the minimum pressure, at which time the piston is freed and allowed to lower at constant pressure. Since Z is the point where all of the gas has changed to liquid, it must be on the coexistence curve, but on PV diagram it is just to the right of point A. It is expected that the examinee will know that the volume of the gaseous state is on the order of 2000 times the volume of the liquid state. Points A and B must be at the correct location in both figures. Points C, D, W, X, Y, and Z must be at the correct location in the RT diagram. Points C and D must be at the correct pressure, but in the V range 1000 to 5000 for the PV diagram for partial credit. Points X and Y must coincide with the C on the PV diagram. Points W and Z must be at the correct pressure, but can be located in the V range 1 to 2 for full credit, but 2 to 5 for partial credit.